Now let's see how we can see the Wick's theorem using path integrals. If you remember the path integrals, the Wick's theorem states that if you have the empty state time-ordered product of your fields at different times, the Wick theorem doesn't need these states. This will be equal to just the normal ordered products of these fields with all possible contractions. Contractions meaning they will be replaced by propagators. Now, in the path integral case, we can show a similar theorem, but we will be using matrix elements. It won't be in operator form. So what we will show is that we will study such a time-ordered product between the empty states. This will be equal to sum over all contractions of these fields. No, not time ordered. Now they are normal ordered products. And since the normal ordering just gives 0 if there are any operators left inside, here there shouldn't be any operators left inside, so it will be this one. Now let's see how we will proceed. Note that this time-ordered product of any operator, we had already seen that this can be written as such a path integral, the phi of whatever operator we have, e to power I from minus infinity to infinity, or let's say just the L0 density. And this is the non-interacting Lagrangian that will be crucial, divided by d phi e to power I L0 d4x. So this is how we define this time-ordered product. Now, before proceeding, let's define one quantity. J will be our function. So we will define this as d phi e to power I L0 d4x plus I j of x phi of x d4x. This is what we will be calling the source term. Now the reason why we define is, let's just take some derivatives of this j, functional derivatives of j. Let me take the functional derivative of this z with respect to j of x1. This will be the measure. The j appears only in the exponent, and when I take the functional derivative of this integral, it will just bring down phi of x1. Well, this is minus I. So it will be phi of x1 e to power I L0 d4x plus I j of x phi of x. And similarly, if I take further derivatives, let's say minus I derivative with functional derivative with respect to j of x1 times minus I the functional derivative with respect to j at x2 of z. Well, this time I will get two phi's, phi of x1, phi of x2, e to power I L0 d4x plus I j of x phi of x d4x. So in particular, if let's say I take this derivative then divide by z and then set j is equal to 0. You see, this derivative over here will be just bring down this phi of x1, phi of x2. Now since j will be 0, this term will be absent. I divide by z, Z itself doesn't contain these, and again I just put j equal to 0, so this term doesn't appear, but what remains is nothing but 0 t time ordered product of phi of x1, phi of x2. And by taking further derivatives, I can calculate the time ordered product of more operators over here. So you see that for me to calculate these matrix elements of these time ordered products, it's enough to calculate J. Now let's look at J. Now to calculate J, well, let me first write it explicitly. Now since I'm doing the scalar field, the L0 Lagrangian density is L0 is 1 over 2 del mu phi squared minus 1 over 2 m squared phi squared. So Z of J is the path integral of the exponent I d4x 1 over 2 del mu phi squared minus 1 over 2 m squared phi squared plus j phi. Now, if this term were absent, then I could convert this to some Gaussian path integral. It's just the Gaussian terms, this one and this one, they are the Gaussians. Now let me try to get rid of this j by a redefinition of my fields. I will define my fields phi as a new phi plus some shift. I'm just essentially making a shift in my variables such that in these new variables, phi is my new variable, there won't be such a linear term. That I would like to choose a delta such that the linear term will be absent. But note that this measure that appears in our path integral is the product of the phi x m t n over all points and time. But this measure, since delta is just a constant shift, this is actually equal to x m t n d phi x m t n. So the measure in terms of my original field is the same as the measure in terms of my new fields. So this is something to keep in mind. So let me just look at this exponent only and replace this this shift in the exponent. So I have d4x 1 over 2 del mu phi squared minus 1 over 2 m squared phi squared plus j phi. This is equal to d4x 1 over 2 del mu, the new field squared, minus 1 over 2 m squared, the new field squared. This is the term I want. But there are additional terms, plus d4x 1 over 2 del mu delta squared minus 1 over 2 m squared delta squared plus j delta. Plus there are also the cross terms, d mu phi d mu delta minus m squared phi delta. Oh, the new field, this is not the old field, the new field. And minus m squared phi delta and j phi plus j times new field phi. Now this last line over here is the term that contains terms with linear phi. There's just a single phi appearing in these terms. So my aim will be, is it possible to choose delta such that this last line is 0? Now let me try to do an integration part in the first term. So I won't have the derivative of phi. I will move this derivative to delta. So if I do an integration by part in the last line, then that term becomes some three-dimensional, four-dimensional surface integral of phi del mu delta minus d4x phi. Well, phi is now common in all of the terms. Let me take out the phi also. Del mu delta plus m squared delta minus j. Now, since delta is arbitrary, I will choose the delta, the boundary condition on delta such that it goes to 0 at the boundary of my four-dimensional space-time. So this term is 0 because del mu delta goes to 0 on the boundary. This is at infinite time, infinite space. And so it's enough for me to ask this expression over here to be 0. So Laplacian plus the Lambertian plus m squared delta should give me j. Now there are a couple of ways to write the solution over here. I can just say that delta is equal to the inverse of this one. Keep in mind that this inverse over here is not the arithmetic inverse, but it's in the operator sense. Or I can, if I define g of x, y, this is the Lambertian in x, g of x, y, this should be equal to the four-dimensional Dirac delta of x minus y. Then I can choose a g which will be also which will satisfy this equation. It will be symmetric under x and y, and it will also satisfy my boundary conditions. In that case, delta of x will be just given by d for y, g of x, y, j of y. And keep in mind g of x, y will be g of y of x. This is just the Green's function of this operator over here. So, assuming I choose my delta to have this form, given by this expression, I know that this term, the last line, this line will be 0. I have the first line, which is nothing but my free Lagrangian density without this source term. And then I have this second line, which is the pure source term. So my integral in j of z of j is now, let's go, there's the measure, but not that the measure in terms of my original field is the same as the measure in terms of the new field. So I can just replace it. Then I will have the, in the definition of z, you see I have these integrals. But we had just shown that for the particular choice of delta we will be making, this is just e to the power exponent of I L0 expressed in terms of the new fields. Well, there's the integral d4x. And then there is the second, this line is still there. We will also simplify this line. This is our z of j. But note that the second line is independent of my field. So I can just take it out of the integral. So z of j becomes the exponent. Well, there's the I, this I d4x 1 over 2 del mu delta squared minus 1 over 2 m squared delta squared plus j of delta. And this is the only thing that remains inside, but I can just rename this phi as my old field phi, but that explicitly shows me that that is nothing but z when j is equal to 0. So z of j over z of 0 is equal to exponent I d for x 1 over 2 del mu delta squared minus 1 over 2 m squared delta squared plus j of delta. Now let me simplify that exponent even further. That is exponent. I will do an integration by part over this term. Now that would give me a surface integral of delta del mu delta minus I d for x. Every term will contain a delta 1 over 2 the Lambertian acting on delta plus m squared delta minus j times delta. This is my new exponent. But due to the boundary condition that delta satisfies, this first term is 0 because delta is 0 at infinity, and I am left with exponent minus I d for x. Remember, the delta satisfies the Lambertian plus m squared acting on delta. It just gives me j. 1 over 2, there is this delta, overall delta. This delta is out. Now let me just, okay, this is the delta is out. So here we have 1 over 2j minus j. So this is equal to the exponent of 1i over 2 d for x delta times j. Now we know what delta is. I can also rewrite this as exponent I over 2 d for x d for y j of x g of x y j of y. This is my z of j divided by z of 0. Now let us take the derivative of both sides with respect to j. Minus I derivative with respect to j of x1 of z of j will be z of 0 times the derivative of this exponent. Well, it will just give me an I d for x g of x1 x j of x times the exponent, which will be just z of j over z0. These will also cancel. So the derivative of z of j with respect to j of x1 will be I d for x g of x1 x j of x z of j. So it essentially brings down such a factor in front of z if I take the derivative with respect to j. Now let's do it once more. j of x1 minus I derivative with respect to j of x2 of z of j this will be equal to, okay, this derivative, well, let me change the order, x1 and x2. We already have calculated the first derivative with respect to j of x1. If I take another derivative with respect to j of x2, no, so there is this I over here, there is a minus I, so there is no I. So it will be a minus I g of x1, x2, z of j. This is the derivative of this term in parentheses, this minus I over here. But then I also have this term times the derivative of z of j. So that will make it a d for x, g of x1 x, j of x, times the derivative of the second term. It will bring another such factor, d for, let's say, x prime, g of x1 x prime, j of x prime, and z of j. So if we set j is equal to now, so minus I derivative is second derivatives, evaluate that j is equal to 0, you say the second line is just becomes 0. So this becomes minus I g of x1 x2 z of 0. But remember our original definition of the time ordered product of phi1 of x1, phi1 of x2. This was given by the second derivative of z of j, all of this divided by z of j, and then we set j is equal to 0. But this, from this expression over here, we say that this is nothing but minus I g of x1 x2. Now, there are a couple of things we should pay attention to in this derivation. You see, when we are taking the derivative of z of j, or let's use this term over here, the derivative of z of j can act on the exponent in z, higher derivatives. It can act on the exponents of z. It brings such a factor in front which contains a j. The second derivative, it could act on this prefactor. So there is a term that doesn't disappear when j is equal to 0, but it can also act on this z of j. So each derivative basically brings such factors which just go to 0 when j is equal to 0. So basically what happened here, the contribution we have is these two derivatives, they both acted on what is in the exponent, and one of them eliminated one of these j's, the other derivative eliminated the other j, so we recover that non-zero value. Now, if we have more than two derivatives, let's say minus I del by del j x1, minus I del by del j x2, minus I del by del j x3, minus I del by del j x4, acting on z of j, and then divide, set j is equal to 0, and then divide by z of 0. If you want to have non-zero contributions, both derivatives should act on the same exponent, and they will give such a factor. So it's possible that if we just take these two pairs, x1 brings down the exponent to in front of z of j, and then x2 just eliminates the other j that remains in that prefactor, and we have just this factor. So that such a contribution will contain minus I g of x1 and x2, and similarly for x3 and x4, one brings down a factor from the exponent, the other one just eliminates the other j in the exponent, so we will end up having g of x3, x4. Or it might be possible that this derivative brings down the factor from the exponent, but this one cancels it. It cancels the j in that factor. In such a case, we will get an additional contribution, x1 and x3, because we are pairing this one and this one, and the other two are also paired, x2, x4. Or it might be possible that this x1 and x4 derivatives, one of them brings the exponent down to the front of the exponent, the other one just cancels the j inside, and that will be a factor minus ig of x3 and x4. So this will be equal to time ordered product of phi of x1, phi of x2, phi of x3, phi of x4. So what this tells me is that if I want to calculate such a time ordered product, I should put as many derivatives, but to get a non-zero contribution when j is equal to 0, I should pair those derivatives, and I should also consider all possible pairings and sum their contribution. Well, the sum basically comes from the fact that the derivative of a product is just the sum of several terms. So this sum brings me all these possible sums. So I should pair these derivatives in all possible ways, and then each pairing will give me a g. Well, g is nothing but the pairing of two fields, and then I should just sum the contributions from all such pairings or contractions. So this is the essence of the Wick's theorem.